Alright, so in this video I'm gonna be explaining another important article which has the title Improved Techniques for Adversarial Discriminative Domain Adaptation. As you see, the measure is still adversarial approach, but it is an improved technique in this paper in 2019. So adversarial discriminative domain adaptation is an efficient framework for unsupervised domain adaptation in image classification, where the source and target domains are assumed to have the same classes, but no labels are available for the target domain. While ADDA has already achieved better training efficiency and competitive accuracy in image classification in comparison to other methods, we investigate whether we can improve its performance with a new framework and new loss formulations. So we first extend the discriminator output over the source classes in order to model the joint distribution over domain and task. We introduce various forms of regularization for stabilizing training, including treating the discriminator as a denoising autoencoder and regularizing a target encoder with source examples to reduce overfitting under a contraction mapping. For example, when the target per class distributions are contracting during alignment with the source. So we are leveraging on the fixed distribution over source encoder and to propose a maximum mean discrepancy. So this is their measure, maximum mean discrepancy for domain adaptation. Comparing and providing a complete analysis of how our method extends over multi-class extension of ADDA and discriminative variants of semi-supervised GANs, including a proposed pseudo-label adversarial loss function that can be viewed as a multi-class version of the inverted label GAN setting. So you see the figure shows the best configuration for training and inference explored in the paper. In step 1, we train them on source dataset only. After that, we train on the target and domains adversarially, so we can remove the problem of domain shift between source and target domains. For example, your source is MNIST data, but your target, as you see, are street view images of numbers. So here we have two target source and target encoder separately, but this one is the same for the source. And then we have this, so we will go through that. Our objective is to substantially improve the adversarial train of target encoder. And so step 1 that I said, we only train on the source classifier, source encoder using source data. So this one is very obvious. The second step is just discriminative loss function. We train the target encoder adversarially by passing the source and target encoder logits to a discriminator. In doing so, we implicitly align the target encoder distribution to that of the source. As the source encoder has fixed parameters, we learn an asymmetric encoding with untied weights. This is an important topic in deep learning. So, which is the standard setting in both ADDA and GAN implementation. In addition, we can improve the convergence properties by first initializing the target encoder weights with the source encoder weights. So, as theoretically proven, for the GAN setting, if the real and fake distributions are disjoint, we are always capable of finding an optimal discriminator, and this leads to instability or vanishing gradients propagated to the generator. By initializing the target encoder rates with the source encoder rates, we ensure the target encoder distribution is not initially disjoint from the source encoder distribution, and there is some initial clustering based on class, which thus stabilizes convergence. We extend the discriminator output to k+1 dimension vector, representing class probabilities, in which the first k dimension represents the joint distribution over source domain and a task-specific class, and that final k+1 dimension is for target domain. And so we denote the k+1 class labels as, so k of them is for source, the last one is for target, where each source encoder is assigned to its task label. However, contrary to semi-supervised GANs, where the discriminator inputs are images, the discriminator inputs and outputs now share common supports over the k-task classes. For the source domain, we can leverage on this fact by effectively modeling the discriminator as a denoising autoencoder, where we can jointly train the discriminator to reconstruct the source encoder logits and encourage the discriminator to potentially learn a more informative representation by corrupting the logits. As denoising autoencoder is an effective method of approximating the underlying source logit manifold and ensures that the discriminator deviates away from learning a simple identity function. We refer to this corruption process, as I said here, corruption process as N, which represents the conditional distribution over the corrupted source encoder logits given the source encoder logit. Therefore, the first term of our discriminator loss function is effectively a reconstruction loss, which we set as the cross entropy between the zero concatenated source encoder posteriors and the discriminator posteriors. So we also apply dropout independently to the target encoder. However, we want to distinguish between the source and target encoded logits. We train the discriminator to assign the k+1 target domain class to the corrupted target encoded logits such that they lie in an orthogonal space to the source domain. In other words, the second term of our discriminator loss function for a target encoder logits is this one, double expectation. So D here is just the case k+1 dimension of D, and the discriminator loss function, this discriminator loss function is thus simply the sum of 2 and 3. And in order to further motivate this reconstruction-based loss, we derive a loss function akin to a discriminative variant to semi-supervised GANs. And for the target encoder loss function, in order to train the target encoder adversarially, we want the target encoder to generate an output that is representative of one of the first k-task specific classes rather than the k+1 target domain class that is assigned when training the discriminator. So to achieve it, we leverage on the two source posteriors. So these are the two source posteriors generated by source encoder and discriminator respectively. Contrary to supervised domain adaptation methods, there are no known source and target pairwise correspondences. And we cannot formulate a paired test over the posteriors. However, we can formulate the problem as a two-sample test by considering the distribution over target discriminator posteriors compared to the distribution over the source encoder posteriors, where our null hypothesis is that the distributions are equal. We considered a target discriminator, so this is our target discriminator posterior, and also a set of source encoder posteriors, and this is our source encoder posteriors. So these two distributions are very important, and N is just the set cardinality, and P and Q are the respective posterior distributions. So we want to maximize the distance between P sub S and Q sub T. The distance between P sub S and Q sub T are the respective posteriors. So we want to minimize the distance between them without performing any density estimation. So to this end, to be able to do this, we adopt the maximum mean discrepancy metric as a measure of distance between the embeddings. And I have a playlist for this reproducing kernel Hilbert space. I have a video, not a playlist, that I explain all of these things. But the important thing is that still we are using this maximum mean discrepancy as our measure to reduce domain shift. And the distribution P sub S over source encoder posteriors is fixed during adversarial training, and as such we are effectively aligning the distribution Q over target discriminated posteriors to P. We again append a 0 to the source encoder posteriors to represent the target domain class probability, such as both source and target posteriors are k+1 dimensional prior to mapping to H. This 0 constraint on the k+1th class acts as a strong prior upon which to learn the target encoder. As such, the source encoder posterior provides a more informative representation than the source discriminator posterior. The feature map in this equation, this feature map, this phi here, the feature map phi here corresponds to a positive semi-definite kernel. And we know the kernel trick. We can always avoid to deal with the features. We just work with the kernels. And the loss function on the target encoder we wish to minimize can thus be written for aligning Q to P. So we opt to use a linear combination of R multiple radial basis function. For example, this kernel is the RBF kernel, and then inference on the target set. So we infer on the target encoder output the class predictions are just the maximum of H, argmax of H. So, and then they talk about transitioning from two heads to one head. The rest of them are the details. But these are the variants of discriminated configuration for adversarial training. You see in A, this represents the standard ADDA everybody knows, just a single discriminator head for classifying the domain. This is, we call it vanilla GAN. But in B, It is multi. This extends with additional task classification head for classifying source examples. This is respectively equivalent to DAN. So now we also have this task here. And in C, it's joint. It means that their proposal in this paper is adapted from the formulation, which will learn a joint distribution over task and domain. So here is just about domain. In multi version of that, we also have class and domain. But here they just jointly do. They combine the laws for the domain and task specific. So that's why it's more interesting, because you can combine it. For example, y equal to 1, 2, same as this one. You're still using it, but you say that which one is source, which one is target. As I said, we have a vector. The last one, which corresponds to k plus 1, is for the target. The rest of them is for the source. That's the major contribution of this paper. And they do this analysis of target encoder loss functions. The difference between MMD and feature is that L feature aligns intermediate features in finite dimensional Euclidean space, where MMD aligns the projected discriminant posterior in infinite dimensional reproducing kernel Hilbert space. Oh, they have a pseudo labeling technique as well here, that they are using, for the sake of completeness. They propose a final discriminative variant for target encoder loss function, inspired by unsupervised GAN training, where the generator is commonly trained with an inverted label objective. For example, inverting the generated label and training with cross entropy. As the inverted label objective is not viable for a multi-class discriminator output, we instead propose a pseudo-label objective for training the target. So this label objective is not viable for multi-class discriminator. So that's why they are using this pseudo-label objective for training the target encoder in the discriminator setting. So the objective draws parallels to unsupervised domain adaptation work that use pseudo-labels. The pseudo-label is taken as the index of the maximum of the first k discriminator logits. So we note that unlike a proposed target encoder loss function that is distribution-based, both inverted label assignment and our pseudo-label assignment are instance-based. This potentially means that they are more prone to instability from noise examples in the training. Even if you do batch of size 1 or size 5, very small batch size, you see it's very noisy. But when the batch size grows, it becomes mature, because it's not affected by just one of them. It looks overall at the overall pictures, and it's very robust. So with the same analogy, they are talking about this idea of instance-based. Pseudo-label assignments are instance-based here, but they are prone to instability. So in order to motivate our proposed adversarial loss functions compared to discriminative variance, we perform an extensive analysis. For example, when we go from source domain, which is street view pictures of digits, to MNIST data, this is a domain adaptation, and they use target regularization as well.